So now I'd like to introduce our second speaker. This is Chris Edwards. He's a professor of mechanical engineering at Stanford University. He is the exergy king. He's taught us all to appreciate the value of the exergy analysis. He performs theoretical and experimental studies of energy transformations to enable the conversion processes to cleaner, more efficient, more controllable than has been possible with traditional technologies. Applications have included advanced transportation, advanced electric power generation with carbon mitigation. He has a master's and PhD from UC Berkeley. He also spent a large portion of his career at the Sandia National Laboratory, where he worked at the really highly regarded combustion dynamics facility. He was also the original deputy director of the Global Climate and Energy Project and had a huge influence on how we think about all these issues. So please join me in welcoming Chris.
So the title of the talk in the program, I think, is the sootless diesel. But the first thing I need to do is tell you that what we're really after is high efficiency. It's not that I'm a huge fan of diesel fuel. I'm definitely a fan of not having soot around. But we want to be efficient, and one of the paths to doing that and doing that in a way that's viable, economic, works hard, generally successful, is to do high temperature combustion, and diesel style combustion, not necessarily with diesel fuel, is a key way to approaching that. This is the work of Greg Roberts and B.J. Johnson, who just finished their PhDs, and the students who are following on are Nat Oliver and Barak Seitoun. The motivation for this really comes from looking at the heavy-duty part of transportation, in that if you look out into the future on the projections, light-duty is looking pretty good, particularly if you think in terms of some of the things that are developing now, electric vehicles, hybrid vehicles, maybe fuel cells if they come along. But the part that worries me is the heavy-duty sector, because we really don't see many new options. It's a tremendous growth area, and in particular, if you think about the world as it develops, what will happen with those economies, this is the way that goods and people get moved around. And so figuring out how to handle this challenge is one of the things that I think is worthy of our time. Okay. If you look at that in terms of what it means for fuels, diesel is the fuel that people think of, but a diesel engine does not have to run on diesel fuel. Diesel fuel is a portion, a cut that you take from a hydrocarbon barrel that's really nice for doing this in the traditional sense, but if you do it in the sense that we do it, where we want really high efficiency, things that you would not think of as being good diesel fuels actually become very nice fuels. In fact, in my opinion, better fuels for a diesel than diesel fuel. So I want to separate the two, diesel style combustion or a diesel engine from diesel fuel. What we need to do, if we're going to try and satisfy this and do it in an efficient a way that fosters development and a way that works for the environment, we have to handle high load. So the reason why the diesel engine is used is the harder it works, the hotter it gets, the more this style combustion likes it. You do this with a spark-ignited engine, you get knock. When you get knock, you pull the spark back, you lose efficiency, you lose power. It's just not really the right thing to do for high load. You want it to be high efficiency. Efficiency is sort of rolled back as we've gotten better at dealing with pollutants. It needs to be clean, of course, and it needs to be affordable, and that's the other challenge, that as you've begun to roll back soot and NOx emissions, that the cost of the after-treatment system has become very high, and so we need a better idea. Okay, so where do we stand in terms of engine efficiency? To the left, you have a spark-ignited gasoline engine. To the right, you have a turbocharged diesel, just mildly turbocharged, and this is pretty much what we have today. Looking in terms of, I can barely see this myself, and I can't read that because of the glasses. I'll pull the glasses off, see if I can do it this way. If you look in terms of the amount that goes into work, this is an exergy breakdown. Exergy is the amount of work you can get from a resource. Then the one over to the left, that's actually modeled roughly on a Prius sitting on its sweet spot. So it would be about 38% efficient in terms of lower heating value, about 36% on an exergy basis. The other is a small bore direct injection diesel, 42 or so on an exergy basis, maybe 45 if you do it on a lower heating value basis. The problem here is the first 20+% of the work potential is gone because you do an unrestrained chemical reaction called combustion. If you do it perfectly, you kill 20% of your work potential just because of entropy generation from the system. That's hard to go after. You can only go after it either by changing from combustion to a restrained reaction, that's what fuel cells do, or by going to extreme states. That was another program that we did for GSEP. You can get about half of that back in a combustion engine. But here's the part that really offends me. It's this part that's in heat transfer. because most of that energy is destroyed as you go across the thermal boundary layer before you even hit the wall. And so that's just got to go. So if you go after that and you attack that with thermal barrier coatings, what are called low heat rejection engines, here's a couple of options for this. If you insulate a bunch of surfaces, so the little graphic down there shows the same stuff that you spray on gas turbines, mostly YSZ, about 1 millimeter, 2 millimeters thick. Onto that, you can cut the heat transfer losses, but you shift most of that energy into the exhaust enthalpy. So you have to be able to take that and extract it somehow. You have to get work out of it. Some of that you can get with a turbocharger, some of it you can get from overexpanding. I'm a big fan of overexpansion because you don't want wickedly hot exhaust hitting the turbine stage on the backside. So to the extent that you can do those linkages, you want to do it. And you can even turbo compound that. If you do that, you get the bar that's over to the left, where we're starting to creep up into some interesting efficiencies in the 50% range. If you pull out all the stops and either do a bottoming cycle that's regenerative, like a steam injection cycle, or you put a full steam bottoming cycle or an organic Rankine cycle, depending on the temperature that you have, then you can move over to the other side and you can get into the mid-60s with this. So really what we're after is how do you get to high efficiency? Reality check, can you do some of these things? You can buy a turbo compounded engine from 2 companies, at least. I don't know, maybe GE's got one lurking in the background there too, you never know with them. Detroit Diesel and Scania both sell them commercially. Lots of people have been looking at how you might package bottoming cycles. GE already does that for their large engines, but whether you can do it on board a vehicle is another question. People are looking at that. There are X-Link overexpansion packages. Honda's not selling it anymore, but they have a really nice geometry that does 1.4 times more expansion than it does compression, which fits nicely. And GE has been spraying YSZ forever on surfaces, so I don't really think that's a huge challenge. If you go after the heat transfer loss, just because I want that exergy back and I want to make it more efficient, this is what it might look like. So different pieces. You definitely want to do the head and the piston for sure. You really got to go after the valves, you got to go after the ports, because you don't want to heat things up before they come in, and you got to transfer that enthalpy to whatever the next extraction stage is on the downside. So it's not just about in-cylinder stuff. But the other thing that you don't really care about, at least in my opinion, is you don't care so much about the liner. There was a big program in the 90s of low heat rejection engines funded by the Army, and it came to a couple of conclusions. Ceramics are really tricky. What are you going to do about the lubricants? And you got to extract this energy out of it, and the combustion was a little hard to deal with. In my way of thinking, you go for about half of the loss. You leave the liner alone. You leave the lubrication alone. You do the upper part, and you can get about half the heat transfer, a reduction of about half, and you redeploy that. How do you do that? You spray stuff on. So some of this is sprayed, some of this is cast. There's a whole bunch of different methods, but those are our valves, bowl and piston, that's our cylinder head, and basically we've got YSZ on those, a couple of millimeters thick. Doing the experiments becomes a little interesting and a little tricky, and it's a little interesting and tricky. We have single cylinder engines. We do all this stuff on a custom cylinder head that can take the pounding, the lack of heat transfer, all the crazy things that we do to it, including putting transducers and injectors in crazy places and all that good stuff. We put the coatings on it and we measure what's going to happen. And it's really good in that it can tolerate all these things and do crazy research stuff. We've got fully flexible injection and VVA and all that stuff. But there's some things that you can't do with a single cylinder engine. One is you can't turbocharge it because it only breathes out once every 4 strokes. It only breathes in once every 4 strokes, and it would be a ridiculously tiny turbocharger that nobody believed the results from anyway. But we can model turbochargers, so we modeled the turbocharger. You'll also notice that we've got tiny little valves compared to a real engine because we've got real estate for fuel injectors and everything else, and we need structural support and all that good stuff. Our intake side, we force feed it, so we're not worried about that, but the exhaust valve is small, so we have a very tight exhaust system. But that's okay, we can model around that too. So we do a combination of experiments and modeling to figure out what will happen. And that's really important. The stuff that you can easily model, we model. The stuff that you can't and you got to go to the experiment, the combustion and the heat transfer. You got to experimentally measure that. So it puts us in kind of an interesting experimental regime. So what do? We integrate those two together. We simulate the turbo machinery and we create simulated intake and exhaust states across it. We boost on the front side according to a compressor map from a turbocharger. We back pressure the exhaust to get the right amount of work with the efficiency on that. So we've kind of boxed in the combustion process in between those two. Then we measure the heat transfer in the combustion process because those are so nonlinear, we're never going to model those with any sort of confidence for that. And we combine it. So we use our modeling to get back to what we think can happen in reality. In order to do that, you have to be able to model things. These are modeled and measured. For the actual experimental stuff, it's not that hard to do. It's not a state-of-the-art thing anymore. I teach people how to do this in class. And so we get two sets of results, the research engine results at the bottom and what they would be in a production engine, sort of reasonable friction, turbocharger, valves, all that good stuff. And if you look, this is one of the cases with turbocharging. We can get the efficiency up about where it would be in terms of what our modeling would say, with a very significant increase in power density. So I don't really like the low temperature strategies. Low temperature strategies are great for some emissions reductions things. They cut heat transfer, but they cut power density. And engines are supposed to work for a living, so I prefer to raise the wall temperatures and raise the combustion temperature inside of it and get more work out of the engine rather than less work out of it. But basically it says that we're on track. We have a little more heat transfer than the 50% reduction that we would have wanted, but it's also sort of Gen 1 thermal barrier coatings and all the rest. For sure, we need to do more extraction. Turbocharging is just the minimum version. Turbo compounding, we've done other experiments, but when you start to have significant enthalpy flows coming out of the back, as the graduate student who did this pointed out, it gets hot. And when it's hot at 1 bar, that's not such a big problem, but when it's 4 or 5 bar and made out of mild steel and starting to creep, you have to be a little bit careful about that. But that's okay. We learned what we needed to learn from that. Okay, what about soot? So I bet when I say diesel to you, that's probably the first thing you think is soot. Either soot or noise or smell or something nasty. That's what I think. I think soot. So here's a lovely graphic of some terrible soot. Here's the 30-second version of where soot comes from. You've got an injector inside the cylinder. You squirt diesel fuel, pretty reactive, into very hot air. It doesn't ignite immediately, so it mixes a little bit, forms a little plume. That plume goes off. Okay? It's called the premixed combustion phase. That's not our problem in terms of emissions. That's a bit of a problem if you talk about knock or being noisy in a diesel, but it's not really our problem. Our problem is when you hog the rest of the fuel in there, the mixing controlled phase. You've got fuel down the middle, the oxygen's on the outside. You've got to get these two to meet each other. If you don't do it, you crack the fuel. Thermodynamically, it wants to become carbon and hydrogen. Right? It's not going to get to thermodynamic equilibrium, but it's on that path, and that's what's driving it. And that's why you're going to make soot. Right. So I want to look at one of those plumes. And if you look at one of those plumes, this shows you everything you need to know. Fuel goes in over there. You suck air in as it's entrained. It makes a mixture that's wickedly rich. That cooks things, makes a whole bunch of little bits, and those bits work their way down to carbon and hydrogen and form that gunky black stuff that's called soot. So it's all inside that plume. So we're going to look at a plume. Over to the left is number 2 diesel fuel. This is in our combustion simulator, our extreme compression device, but not being as extreme as we normally are. Number 2 diesel fuel, so a single jet out of an injector, you would normally have 4, 6, or 8 of these going into the bowl. And so you see that bright, sooty, that's radiation, thermal radiation from hot soot particles inside of it, and that's why we have soot problems. Probably the easiest thing to do in terms of having diesel-style combustion and not having soot is make sure that the oxygen-carbon ratio is unity. If the oxygen-carbon ratio is unity, you can be pretty sure you can avoid soot. The cheapest way to do that is to hang an oxygen in the middle of the fuel chain. It's got to be in there so that when you break the bonds, the oxygen is available. Methanol is an easy way to do that. Here's methanol on the right. Most people think methanol is not a good diesel fuel because it takes a very high temperature for it to auto-ignite. We make high temperatures. You could give me your suntan lotion and I'll get work out of it in this engine. Okay. So methanol becomes a nice fuel. All kinds of things that you think are not nice fuels are actually very nice diesel fuels. I think they're better than diesel fuel. Methanol does form soot, so the idea that it is a sootless fuel is incorrect. If you rearrange the exposure so you look more carefully, this is very, very clean, no additives, reagent grade stuff. But you look a little more carefully at it. In the middle of the chemical soup, you will form soot, but you also burn the soot back up again. And that, of course, is the key, is to not have any net soot out. You'd also like to not have the soot so you don't have the radiation heat transfer losses, but that's sort of a secondary effect. So there are some ways to go about this. In order to figure out what happens, you need to actually measure this. Way too complicated to model. If you look at diesel and you look at methanol, you did this some time ago. Diesel, as you go richer and richer, put more and more fuel into the charge, higher load conditions, you're going to make more and more soot. Traditionally, you would be limited at around 0.7, 0.75 equivalence ratio because you make that big black cloud and your combustion efficiency goes down. You would say you can't run the engine there. That would be inappropriate. The limit is down there. So, diesel is just kind of off the map unless you put a diesel particulate filter and what you're going to need to do for the NOx and all the rest of this. If instead we zoom up or zoom down by a factor of 100, so that the standard is now up at the top of the page over there, we've got methanol and ethanol. And over the typical range that you might run a diesel, a factor of 10 below what the standards are. The nice thing about that is that if we push out from there to stoichiometric, we're still a factor of 10 below the standards. We're basically in our measurement limit for the methanol, and we're a factor of 2 below even for ethanol. So now we've gone 2 carbons to 1 oxygen atom and something that is deployed. Now it's true, there's not a lot of E100 out there, and that's what we're using here. Personally, I'd rather have wet ethanol. It'll be interesting to see whether we can do this with E15. But that's, I think, going to be for Barak to figure out. But the reason for doing that is if you can go all the way to stoichiometric operation, it means you get to use a 3-way catalyst for NOx control. And that's the same 3-way catalyst that's on your car, and it's pretty darn cheap compared to an SCR and a DPF system. So that's what we're after. The other thing that comes along with that, well, combustion efficiency is still high. If you care about that, I'll talk to you more about that later. The other thing that comes along with pushing to stoichiometric is you get 30% more work out of the engine. So you don't go to half the power density, which is what you get with LTC approaches. You get 30% more power from the engine, from the base engine in doing this. So I kind of like that. I think that's a good thing. Okay, where do we stand on all this? So methanol and ethanol we've looked at, and what we mean by, quote, sootless, nothing is sootless. Sootless is whether or not you're well below what the limit is. So that's how I'm using the term here, but I don't think anything is particularly sootless in these conditions. So that we've seen. Interesting thing, we lost a picture in there. Now that's neat. Where did the methane picture go? Okay, well, that was a picture of methane. And the picture of the methane looks a lot like the methanol and ethanol picture. So while we haven't run it yet and done measurements, which Nat will do, wherever Nat is, that's probably going to be down where it's below the sootless limit. It's not the oxygen in that case, it's the hydrogen-carbon ratio. It's the hydrogen atoms in that. But that provides an interesting thing, both in terms of the interest in terms of natural gas and a really nice test bed in terms of looking at the 3-way catalyst. How do you do the control? How do you do the combustion shaping and get the stoichiometry right for balancing off the NOx emissions, which is part of our overall strategy. Next step, you might say, why on earth are you interested in normal propanol? Just because we're talking about 3 carbons to 1 oxygen. So pushing this to make more and more soot on the margin so you can then work on techniques to mitigate what's going to happen on the margin. Natural gas is not methane. It's got heavier stuff. It's got some C4s in there, things that are going to produce soot. Even the ethanol is only a factor of 2 off the limit. But when we're down in that region, what can we do with multiple injections, some of the other approaches to get us down below where we need to be again? So that will be Barak's challenge for that. So a couple of conclusions. Combustion can be made sootless, diesel-style combustion. Just don't use diesel fuel. Or if you use diesel fuel, make it into something else. I think John might mention that in his talk later on today. Transform it to another kind of fuel, like syngas. Efficiencies greater than 60% are possible. Now that's sort of a fuzzy statement. Greater than 50% without being too crazy. Going over 60%, you got to get into bottoming cycles and highly regenerative sorts of things, or do something completely different. It can be made stoichiometric if you want to go there. If you go to stoichiometric, you can go for an inexpensive 3-way catalyst. You already have to have an oxidation catalyst on the vehicle anyway for CO and hydrocarbons, so why not go 3-way for that? And if that's the case, the output goes up by about 30%, and the cost goes down by about 30%. And that's based upon heavy-duty, big rig, DPF plus SCR systems, significant fraction of the cost, 30% of the cost for one of those engines. There's the alcohols, there's natural gas, dimethyl ether, which is the easiest one. You don't have to be high temperature for that, but we're high temperature anyway, so these all become nice things for us. Syngas by in situ reforming, and probably some other interesting things could all be sootless fuels. So, yeah. Okay. I think this is the only GSEP talk I've given that was actually on time in 15 years.
Here comes the layman again. You're saying that you can make it sootless by changing the fuel. That's basically getting away from diesel, reducing the carbon density in the. Okay, now.
Yep.
Could you go back to the diagrams where you showed the ethanol, the methanol, and the ethanol being injected? Yeah.
These?
That works.
Sure.
Now, do I interpret this right that the fuel around the flame is a hydrocarbon that is not being combusted?
So right down the center of each of those plumes is the fuel. The air is on the outside.
Say that again, right down the
Down
center.
the center of the plumes.
Where the bright light is.
Yes. Yeah,
That's the combustion of the fuel.
So hold on. So over to the left is the injector. So it's shot a jet out this way.
Right.
That sucked air in, which has made that big plume.
Right.
Right. Down the center of it is lots of fuel. There's air on the outside. They're finding each other, and stuff's cooking inside of it without oxygen, making soot, and the soot's bright yellow because it's hot, radiating soot.
Okay, but what's the blue?
The blue is a laser. That's Schlieren, so you can actually see the motions in the gas.
What is that blue? Is it a uncombusted fuel?
It's air.
It's air.
You're seeing the air because of a blue laser that's going through, that's diffracting, refracting based on density gradients. So you get to see the air motions.
What's creating the soot? I presumed, and maybe incorrectly, that the soot from diesel was being created by not as efficient a combustion as from ethanol or from methanol.
Yeah, that was my 30-second explanation of where soot comes from. Probably not the best in the world. Go back. Wait. Okay. So liquid comes in from the side. It vaporizes. It transfers momentum to the air, which sucks air in. So from the left-hand side, we've got fuel running down the middle, sucking air in, making an equivalence ratio, a local air-fuel ratio that's like 4 times as much as you want fuel to the amount of air. So it's really rich inside. And that stuff is hot. That stuff cracks, and it goes off to start making soot.
Well, I guess, if what I'm asking myself is why don't you change the shape of the fuel and air and ignition, the premixed flame coming in?
Perfect. So a lot of what you do is you try to do clever things with holes and separations to get higher entrainment rates or change the liftoff of all that. And all of that is the kind of stuff that you can do to make changes to the system. They will not be big enough to get diesel fuel to be sootless. You need to do something much, much bigger. But those are the kinds of things that we'll need for dealing with variability in natural gas, E85, those kinds of things, I think.
I was assuming that...
And there's lots of work on that going on.
I'm not quite sure of this statement, but with the very low cost of methane, I presume methanol would be cheaper fuel to make. I'm not sure that's true, methanol. From natural gas.
So it's a pretty straightforward one to make, and there have been lots of arguments about the economics of that, even for small site, kinds of stuff too. Yeah. I think the bigger question is just the whole infrastructure one, right? Whether or not we're willing to commit to a methanol infrastructure.
All right, thank you.
Thank you. I was wondering if you'd had a chance to evaluate Eddie Sturman's diesel in Colorado. He's well in the 60s% using very precise digital valves that let him do unusual and even multi-event combustion sequences with quite different mechanics than a conventional diesel.
Yeah, so there are systems that can get to high efficiencies. They're typically combined cycle systems that get to those efficiencies, not simple cycle systems. Well, I doubt that, but I'll be happy to look at it.
A quick question, Chris. You talked about many different oxygen-containing compounds. You talked about methane. Would you like to elaborate if there's any chance LPG could be used? So that's propanes and butanes. And it's particularly because there seems to be a large amount of LPG available at depressed pricing today.
Yeah, I think you're already kind of in the normal hydrocarbon kitty by the time you get to LPG, that things aren't going to look that different. I got to say, my aspiration for that is to take it and make it something else on board, do thermochemical recuperation and make syngas out of it, which I'm pretty sure is going to be sootless. We'll have to show that. We've done the preliminary stuff on it, but you actually have to put it through an engine and measure it to do that. But part of what, I don't know, will you talk about that, John, or not? So there's another branch to this, which is take the fuel that's easily deployable and that's economic and use waste energy. We always have too much thermal exergy in the exhaust, and you can drive thermochemical recuperation reactions to do that. Now that's a non-trivial thing, the temperatures and pressures that are required to do that. But making syngas is an upgraded fuel. It's already carrying the oxygen on the carbon, and so it's a really nice fuel.
Follow on to the question the gentleman asked. On the chart here, you show essentially a line injection, and it turns into a cone with the air addition. If that was to change into a plane, hypothetically, suppose the injector is actually able to move fast enough to where the injection is done as a plane, would that reduce soot?
Yeah, that kind of drops your three-dimensional mixing to two-dimensional, so I don't think that helps you. On the other hand, anything that causes you to have something that's spread out and can engage the air better before the reaction zone develops around it is the key to dropping that equivalence ratio. And all that's really good stuff. So there's a ton of research going on now. I mean, that's state-of-the-art stuff that's happening with it. I don't think any of it is close enough to making the reductions that you need to be able to get rid of the DPF and do the kinds of stuff that we want to do while raising the efficiency. But that's speculation on my part.
Would your assessment of diesel combustion be different for synthetic diesel from Fischer-Tropsch, which is primarily alkanes, linear alkanes?
No, if anything, it tends to be a little trickier because the cetane numbers are higher, so it's going to react faster, so there's going to be less entrainment. But for the same reason that I don't think it's going to be subtle things that do it. We need to get close enough to the margin that subtle things can fix things. That's well into the kind of normal diesel range. I used to do a lot of stuff with Fischer-Tropsch diesel, and it's a really nice fuel compared to normal diesel fuel, but relative to where it needs to be to get rid of diesel particulate filters, it's not close.